You hear about comets, bright tails, icy visitors, predictable orbits. But 3I Atlas is different. It came from another star system, traveled for 4.6 billion years, and when astronomers tried to map it with planetary radar, the tools fell silent. Too far, too fast. Beyond the reach of technology that tracked hundreds of near-Earth asteroids, what does that distance tell us? Why does it matter that radar cannot touch this object? And what secrets hide in a comet we can only study from afar? On July 1st, 2025, a telescope in Rio Hurtado, Chile caught something unusual. The Atlas survey system, designed to spot potential Earth threats, flagged an object 420 million miles from the Sun. Not the distance that raised alarms, the trajectory did. Astronomers named it 3I Atlas. The I stands for Interstellar. The 3 marks it as the third confirmed visitor from beyond our solar system. Before it came 1, I Oumuamua in 2017, and 2, I Borisov in 2019. Each one reshaped what we thought we knew about objects drifting between stars. 3I Atlas moves at 61 kilometers per second relative to the Sun. That is 137,000 miles per hour. Its orbit is hyperbolic, with an eccentricity of 6.1 Feingarm, the highest ever recorded. Eccentricity above 1 means an object escapes the Sun's gravity. It never comes back. When astronomers traced its path backward using data from the Gaia Space Observatory, they looked at 93 stellar encounters over billions of years. None of those encounters changed its course enough to explain where it came from. The thick disk of the Milky Way, that is where it originated. A population of older stars with lower metal content, 4.6 billion years old, older than most objects we have ever studied up close. The closest 3I Atlas will approach Earth is 1.8 astronomical units. That is about 270 million kilometers, or 170 million miles. For perspective, the Moon sits 0.0026 AU from Earth. Mars, at closest approach, reaches 0.37 AU. 3I Atlas will not come within even 2 AU. By December 19th, 2025, it reaches that minimum distance, already behind the Sun from our view by then. On October 30th, 2025, it makes perihelion, closest approach to the Sun at 1.36 AU, just inside Mars orbit. Between Earth and Mars, but never threatening either planet, it passes Mars on October 3rd at 0.19 AU, about 28 million kilometers or 18 million miles. Mars orbiters will watch it. ESA's Mars Express and ExoMars Trace gas orbiter. NASA's Mars Reconnaissance Orbiter, even Curiosity and Perseverance rovers on the surface will attempt observations, but radar will not reach it, not from Earth, not from anywhere. Planetary radar operates on principles that seem simple until you examine the math. You transmit radio waves at an object. Those waves travel at light speed, hit the target, bounce back, travel the same distance again. The radar equation shows echo strength drops with the inverse fourth power of distance. Double the distance, echo power drops to 1/16th. Triple it, drops to 1/81st. The Arecibo Observatory in Puerto Rico, before it collapsed in December 2020, was the most powerful planetary radar system on Earth. 305 meters across, transmitting at S-band, 12.6 centimeter wavelength. When it operated, it could detect main belt asteroids and provided the most sensitive planetary radar capabilities available. Arecibo was 15 times more sensitive than Goldstone, but Arecibo is gone. What remains is Goldstone's solar system radar in California. 70-meter dish, 500 kilowatt X band transmitter at 8,500 megahertz. Goldstone detects about 50 near-Earth asteroids per year, provides Delay-Doppler images with 3.75 meter resolution for objects smaller than 50 meters across. Over 430 near-Earth asteroids detected with radar by March 2003, but Goldstone has limits. The radar return signal strength depends on several factors: transmitted power, antenna gain, wavelength, target radar cross-section, distance to the fourth power in the denominator, system losses. For Goldstone, transmitting at 500 kilowatts with its 70-meter antenna, you can detect a 1 kilometer object at a large fraction of 1 AU, but that fraction shrinks fast. At 8 to 10 AU, the distance to Saturn, you need targets hundreds of kilometers wide. Practical detection range for small objects like comets rarely exceeds 0.3 AU when conditions are good. Most radar-detected comets were observed within 0.2 AU or closer. Only 7 comets have ever been detected by radar. Comet IRAS-Araki-Alcock in 1983, Comet Halley in 1986, Comet Griggs-Skellerup, Comet Encke, others all came close, very close. Comet Iris, a rocky Alcock passed within 0.031 AU of Earth. That is about 4.6 million kilometers. Even at that proximity, detecting its nucleus required every bit of sensitivity Arecibo could muster. The radar albedo of cometary nuclei ranges from 4% to 10%, among the lowest values for solar system objects. Lower than most asteroids, the icy dusty surfaces scatter radio waves poorly, most energy absorbed rather than reflected. 3I Atlas at 1.8 AU minimum distance sits 6 times farther than the practical limit for cometary radar detection, even with Arecibo operational. With only Goldstone available, the sensitivity gap widens to 90 times less capable at that range. 2I Borisov, the previous interstellar comet discovered August 30th, Spectra 2019, came no closer than 1.9 AU to Earth. December 2019, closest approach. Scientists stated clearly in published research that the comet did not come close enough to use radar to directly determine its size and shape. Radar was never attempted. The distance prevented it. 1I Oumuamua passed within 0.22 AU of Earth in October 2017 for about 33 million kilometers, or 21 million miles, 85 times the Moon's distance. Even at that range, closer than 3I Atlas or Borisov, no radar observations were conducted. Oumuamua was discovered on October 19th, already moving away from the Sun at high speed. By the time astronomers confirmed its interstellar origin and coordinated observation campaigns, it had moved beyond effective radar range. It was traveling too fast, too far, and nobody had expected an interstellar visitor. The window closed before radar could be scheduled. If you value documented space science and interstellar research like this, subscribe. It is the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's official Comet 3I Atlas page, published October 2nd, 2025. The European Space Agency's frequently asked questions document on 3I Atlas. Peer-reviewed radar astronomy literature from the Arecibo and Goldstone systems published in Science Direct and verified by the Jet Propulsion Laboratory, Asteroid Radar Research Archive, and the August 25th Science. 2025, preprint paper by Martin, Ekordner, and NASA Goddard. Space Flight Center team detailing JWST NIR spec observations. Available on ARCHIV identification 2508.18209. These are not popular science summaries. These are the primary sources that planetary scientists use to calculate detection limits and analyze interstellar objects. Now back to the information. The math tells the story that intuition misses. Radar power drops as 1 over r to the 4th. If an object at 0.1 AU returns a signal strength of S, that same object at 1 AU returns S divided by 10,000. At 2 AU, S divided by 160,000. 3. I-Atlas at minimum approach of 1.8 AU would produce a return signal 324 times weaker than if it were at 0.3 AU, the outer edge of practical comet detection range, even under ideal conditions, and 3I Atlas is not at minimum approach yet. When discovered on July 1st, 2025, it set 4.5 AU from the Sun, 670 million kilometers, or 420 million miles from Earth. At that range, the inverse fourth power relationship means a radar echo would be 41,000 times weaker than at 1 AU, over 10 million times weaker than at 0.1 AU, even if you pointed Arecibo's full 305 meter aperture and megawatt equivalent power at it. The returning signal would drown in noise. No echo, no detection, no data. Goldstone observes asteroids primarily within lunar distance for imaging and slightly beyond for detection. Lunar distance is 0.0026 AU. Near-Earth asteroids detected by Goldstone in the last 3 years tripled compared to the previous decade, with roughly 400 observing hours per year dedicated to asteroid work. But most targets are much closer than Mars. The asteroid Bennu, target of the OSIRIS-REx sample return mission, was observed by Goldstone and Arecibo in 1999 and 2005 when it passed within reasonable range. Those radar observations provided shape and size data critical to mission planning. Bennu is 500 meters across. Even at its closest approaches, radar struggled to resolve surface detail. Imaging required multiple observation passes and sophisticated Delay-Doppler processing. 3. I-Atlas has an estimated nucleus diameter somewhere between 440 meters and 5.6 kilometers, based on Hubble Space Telescope observations from July 21st, 2025, most likely less than 1 kilometer. The upper limit of 5.6 kilometers comes from Hubble images that constrained but could not directly resolve the nucleus, obscured by the coma. If the nucleus is at the smaller end of estimates, around 440 meters to 1 kilometer, it ranks with small, near-Earth asteroids that require close approaches of 0.05 AU or less for useful radar imaging even with Arecibo at full power. The loss of Arecibo in December 2020 represents a massive blow to planetary defense and deep space radar astronomy. Arecibo could observe objects that Goldstone simply cannot detect. 15 times more sensitive, could watch main belt asteroids at 3 times the distance to Mars, could measure rotation rates, shapes, surface properties, binary companions of objects well beyond Earth's immediate neighborhood, could provide decades of advance warning for potential Earth impactors by refining their orbital parameters with precision no optical telescope can match. Ed Lu, former NASA astronaut and executive director of the B612 Asteroid Institute, called Arecibo's loss a major blow to planetary defense capability. A single-point failure, he said. If Goldstone breaks at the wrong time, you get nothing, no redundancy. Patrick Taylor, who heads the Radar Astronomy Division at NSF's National Radio Astronomy Observatory, stated that asteroid or comet impacts are maybe the one natural disaster you can prevent if you know about it soon enough. Radar gives the distance measurement and velocity data that optical observations cannot provide with comparable accuracy. Optical telescopes measure position in the sky. Parallax estimates distance, but uncertainly when targets are small, dim, or poorly illuminated. Radar directly measures distance by timing signal round trip and provides Doppler velocity from frequency shift. Combined optical and radar observations allow orbit predictions decades or centuries into the future. Without radar, uncertainty grows. For 3I Atlas, distance eliminates radar entirely. Goldstone cannot detect it. Arecibo, if it still stood, could not detect it. Even if you built a radar 3 times more powerful than Arecibo, inverse fourth power math still keeps 3I Atlas beyond reach. At 1.8 AU, you would need a transmitted power increase of over 10,000 times, and antenna gain increases proportional just to match signal strength from a 0.1 AU target. No facility on Earth or in space has that capability. No facility planned for the next decade has it. Next generation radar, NG radar, proposed to use the Green Bank telescope as transmitter and the Very Long Baseline Array as receivers, distributed across the continental United States and territories. Potentially much more sensitive than Arecibo, but still in planning stages. Not operational, not ready for 3I Atlas, and even Non-Radar would face the same inverse fourth power constraint. More sensitive means detecting smaller or more distant objects within a certain range envelope. It does not rewrite physics. It shifts the limit outward, but the limit still exists. Why does radar matter so much? Because radar provides information no other remote sensing technique can match. Optical telescopes show brightness, color, spectral lines. You infer composition from reflected light or emitted gas signatures, but you cannot see the nucleus directly if a coma obscures it. You cannot measure the size accurately. You cannot determine if the object is a single body or a contact binary, 2 objects held together by weak gravity. 15% of near-Earth asteroids are binary systems. You cannot determine rotation period unless the brightness varies enough to show light curve features. You cannot measure surface roughness, slope distributions, boulder sizes, crater counts. Radar gives you shape, rotation, surface texture, true size, compositional clues from radar albedo and polarization ratio. Delay-Doppler imaging can resolve features as small as a few meters on objects close enough. For comets, radar can distinguish the nucleus from the coma because grain halos scatter radar differently than solid ice and rock. Coma is optically thick to visible light, but optically thin to radio waves. Radar sees through, measures the solid nucleus underneath the gas and dust, provides unambiguous size estimates not dependent on models of dust scattering or coma brightness. This matters enormously for understanding what the object is made of, how it formed, whether it poses any threat if it were on a collision course. 3. Atlas offers no such data. Distance seals the nucleus away from radar interrogation. What remains are optical and infrared observations. NASA's Hubble Space Telescope imaged 3I Atlas on July 21st, 2025, when it was 277 million miles from Earth. Hubble revealed a teardrop-shaped cocoon of dust coming off the nucleus. The coma. Hubble captured a dust plume ejected from the sunward side and hints of a dust tail streaming away. Hubble's observations allowed astronomers to estimate the nucleus size by observing how much light scattered off the coma and inferring the central body from that envelope. Upper limit 5.6 kilometers diameter, lower limit 440 meters. Most likely diameter less than 1 kilometer based on dust loss rates and brightness, but Hubble could not see the nucleus itself. Too small, too dim, buried in coma glow. On August 6, 2025, the James Webb Space Telescope observed 3I Atlas using its near-infrared spectrograph, NIR spec. Webb works in infrared wavelengths from 0.6 to 5.3 micrometers. Those wavelengths let Webb detect molecular emission lines from gases in the coma. Webb found carbon dioxide, water, ice, carbon monoxide, carbonyl sulfide, all glowing in infrared as sunlight heated the comet and ices sublimated. Webb provided detailed spectroscopy, breaking light into component wavelengths to identify each molecule by its unique signature. Revolutionary data about composition, but still no direct size measurement of the nucleus. The coma still obscures it. Estimates from JWST observations in August 2025 calculated that 3I Atlas was emitting 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, and 0.43 kilograms of carbonyl sulfide per second. Those outgassing rates let scientists calculate how active the comet is. Backtrack to estimate nucleus size from models of sublimation physics. But models have uncertainties. Surface area exposed to sunlight, ice fraction versus rock and dust, porosity, thermal inertia, rotation rate affects which parts heat up. Activity asymmetries complicate things. Sunward side, more active. The emission rates give clues. They do not give direct measurements. Radar would delay. Doppler imaging would show the shape in 3 dimensions, measure dimensions along multiple axes, catch rotation period from how the echo spectrum changes. Not available for 3I Atlas. Will never be available. It passes through our system once, never returns. Hyperbolic trajectory. Escape velocity reached long before discovery. Now leaving. In March 2026, it passes Jupiter at 0.36 AU from the giant planet. Then out past Saturn, Uranus, Neptune, into the dark between stars. Gone. The distance that prevents radar from reaching 3I Atlas is the same distance that tells us how rare these close approaches are. Interstellar objects are common in the galaxy. Estimates suggest thousands pass through the inner solar system every year, but most are too far, too dim, too fast to detect. Telescopes like Pan-STARRS, Atlas, and the upcoming Vera C. Rubin Observatory scan the sky looking for moving objects. Detection depends on brightness. Brightness falls with distance squared. An object twice as far is 1/4 as bright, 3 times farther, 1/9 brightness, below detection threshold, invisible. Most interstellar objects slip past unnoticed. We caught 3I Atlas because Atlas looks deep, scans often, covers large areas of sky, pure luck and improved technology. Before 2017, no interstellar object had ever been confirmed. We lacked the survey capability, now we find them. 1I Oumuamua, 2I Borisov, 3I Atlas, Vera Rubin Observatory. Scheduled for first light in 2026, will survey the entire visible sky every few nights. Expected to detect 1 interstellar object per year on average, maybe more. That detection rate tells us they are out there, constantly, everywhere. The galaxy full of debris ejected from planetary systems during their violent formation phases. Gas giant migration scatters planetesimals. Close stellar encounters strip material from Oort clouds. Supernova shock waves blow lighter bodies into interstellar space. Over billions of years, the galaxy fills with wanderers. 3I Atlas drifted for 4.6 billion years before encountering our sun. That is slightly older than the solar system itself, which formed 4.567 billion years ago. Its trajectory traced back through the thick disk of the Milky Way shows vertical excursions from the galactic plane consistent with an old population. Stars in the thin disk where the sun resides have a scale height of about 1,000 light years. Thick disk stars extend several thousand light years vertically because gravitational perturbations over billions of years scatter them. 3I Atlas. Vertical motion through space indicates it came from that older, thicker population. Lower metallicity stars formed when the galaxy had less heavy element enrichment than now. Its parent star, wherever it was, possibly no longer exists. Low-mass red dwarfs live trillions of years. Sun-like stars live 10 billion. Massive stars burn out in millions. If 3I Atlas came from a massive star system, that star might have gone supernova billions of years ago. If from a sun-like star, that star might still shine somewhere in the thick disk, 5,000 light years above or below the galactic plane. impossible to identify among billions of candidates without more data. If from a red dwarf, that star could survive another trillion years, dim and cool, drifting slowly through the Milky Way, never knowing the comet. It lost 4.5 billion years back, found a solar system to visit briefly. One, Oumuamua, by contrast, originated from the thin disk with an estimated age of about 1 billion years based on its vertical excursion when trajectories were integrated backward. Younger population, recently ejected. 2, Borisov showed intermediate age, about 1.7 billion years, also from the thin disk. The diversity in ages suggests interstellar objects are ejected throughout galactic history, not just from young newly formed systems, not just old disturbed systems. All stages of planetary system evolution contribute to the interstellar population. Some objects drift for eons. Others cruise through in a few tens of millions of years. 3, Atlas happens to be ancient, a relic from when the Milky Way was younger, carrying ice and rock that condensed from a protoplanetary disk billions of years before life arose on Earth. The chemical composition of 3 Atlas captured by JWST stunned researchers. Carbon dioxide dominates the coma. The carbon dioxide to water mixing ratio is 8:1, highest ever observed in any comet. Most solar system comets show carbon dioxide to water ratios below 1. Long period comets from the Oort cloud typically range from 0.01 to 0.1 depending on heliocentric distance. As a comet approaches the Sun, carbon dioxide sublimates at greater distances than water ice because carbon dioxide has a lower sublimation temperature. So closer in, water starts to dominate as carbon dioxide depletes. 3 Atlas at 3.32 AU. When JWST observed it should have shown water beginning to increase relative to carbon dioxide. Instead, carbon dioxide overwhelms everything. 8 times more carbon dioxide than water. 16 times higher than expected for an object at that distance. Only one other comet in the database approaches that ratio, C 2016 R2, an unusual Oort cloud comet also rich in carbon dioxide and carbon monoxide, but even C 2016 R2 does not match 3 Atlas. This is unprecedented. What does it mean? 2 primary hypotheses. First, 3. Atlas formed in a region of its parent protoplanetary disk beyond the carbon dioxide frost line. The frost line is the distance from a star where a particular volatile substance freezes. Water ice line sits around 3 AU in our solar system. Carbon dioxide ice line farther out, around 10 to 15 AU, depending on disk density and star luminosity. If 3 Atlas formed beyond the carbon dioxide line, it would incorporate abundant carbon dioxide ice during accretion. Water ice also present, but less concentrated because water preferentially condensed closer in. Comets in our solar system mostly formed in the region between Jupiter and Neptune, or in the outer disk that became the Kuiper Belt in Oort cloud. That region was cold enough for water ice, but not uniformly rich in carbon dioxide everywhere. Most carbon dioxide in the early solar nebula got incorporated into gas giants, or blown away by solar wind, before it could freeze into small bodies. 3 Atlas's parent system might have had different dynamics. Slower migration, less vigorous disk clearing, more material lingering at larger distances where carbon dioxide ice concentrated. Second hypothesis, radiation processing. 3 Atlas drifted through interstellar space for 4.6 billion years. Cosmic rays bombarded it constantly. Galactic cosmic rays are high-energy protons, atomic nuclei, electrons accelerated by supernova remnants and other violent processes. They penetrate matter, break molecular bonds, ionize atoms. Over billions of years, this space weathering alters surface chemistry. Water molecules can be destroyed preferentially if hydrogen escapes more easily than oxygen. Carbon compounds can be created or enhanced from rearrangement of existing material. Laboratory experiments show that irradiating icy mixtures creates complex organic molecules and can preferentially destroy water ice over carbon dioxide ice depending on conditions. If 3 Atlas accumulated a radiation-processed crust during its long journey, that crust could be rich in carbon dioxide and depleted in water compared to the pristine interior. As the comet nears the Sun, the surface heats. The altered crust sublimates first. Carbon dioxide pours off. Water trapped underneath does not reach the surface as easily because carbon dioxide sublimes at lower temperatures and carries less heat into the interior. Thermal modeling suggests that if the nucleus has low thermal inertia, heat penetration is limited. Carbon dioxide near surface sublimates. Water deeper inside stays frozen. You get a high carbon dioxide to water ratio in the coma, even if the overall composition is more balanced. Radar could test this. Measure the true size of the nucleus. Compare expected sublimation rates to observed outgassing. constrain density and porosity. Not possible at 1.8 AU. The carbon dioxide enigma is not just a footnote, it is the headline. An 8-to-1 ratio of carbon dioxide to water is more than an anomaly. It is a direct challenge to the standard model of cometary formation, a model built entirely on specimens from our own solar system. It forces us to ask a question we have never had to seriously consider. How different can a planetary system be? The two leading hypotheses for this chemical imbalance, formation location and radiation processing, are not mutually exclusive, but each one pulls us down a different path of cosmic speculation, painting a picture of a birthplace and a journey fundamentally unlike our own. Let us first walk the path of formation. If 3, I-Atlas is a pristine relic, its composition a direct snapshot of its birthplace, then it must have formed in an exceptionally coldy, carbon dioxide-rich region of its native protoplanetary disk. In our solar system, the water snow line, the point where it becomes cold enough for water vapor to condense into solid ice, lies roughly at 3 astronomical units near the asteroid belt. The carbon dioxide snow line, however, is much farther out, perhaps 10 to 30 astronomical units, depending on the luminosity of the young sun. For a comet to be composed of 8 times more carbon dioxide ice than water ice, it would have had to form well beyond that carbon dioxide snow line in a region where gaseous carbon dioxide was the dominant volatile available for freezing. This implies several possibilities about its parent star system. Perhaps the star was much hotter and more luminous than our sun. A massive O-type or B-type star would push all the snow lines much farther out, creating a vast, cold outer disk where carbon dioxide-rich bodies could form in abundance. But such stars live fast and die young, exploding as supernovae in mere millions of years. For 3 I-Atlas to be 4.6 billion years old, its parent star must have been long-lived. This points toward a star more like our sun, or even a smaller, cooler red dwarf. If the star was a red dwarf, its habitable zone would be huddled close, and its frost lines would be much nearer than in our system. However, the dynamics of disk chemistry around such dim stars are poorly understood. A more compelling scenario for a sun-like star involves the disk's structure and evolution. Perhaps, in its home system, the gas giant planets, if any existed, migrated differently. Perhaps there was no grand tack migration like Jupiter and Saturn are thought to have undergone, a chaotic journey that stirred and mixed the contents of our solar system, flinging water-rich bodies from the inner disk into the outer realms and vice versa. 3 I-Atlas may have formed in a quiescent, unperturbed disk where chemical gradients remained sharp and distinct. It formed in the deep freeze, stayed in the deep freeze, and was then gently ejected. A perfect sample of a region our own comets only vaguely represent. Then there's the second path, the darker and longer one, the path of a 4.5 billion year voyage through the interstellar medium. The galaxy is not empty. It is filled with a tenuous bath of high-energy cosmic rays. For billions of years, 3 I-Atlas was subjected to this relentless bombardment. Cosmic rays, primarily protons and helium nuclei accelerated to near light speed, penetrate the surface of an icy body to a depth of several meters. This steady irradiation is a form of cosmic chemistry lab. It breaks the strong bonds of water molecules, H2O. The lighter hydrogen atoms can more easily escape to space over geologic timescales, while the heavier oxygen atoms may remain, recombining with other elements. Carbon-bearing molecules like methane or carbon monoxide, also frozen in the nucleus, are similarly broken apart and reformed. Over billions of years, this process could create a chemically altered crust, a weathered rind that is depleted in water and enriched in more complex, carbon-rich species, including carbon dioxide. When 3 I-Atlas finally entered our solar system and began to warm, this irradiated crust would be the first layer to sublimate. The outgassing we see with the James Webb Space Telescope would not be representative of the comet's bulk interior, but rather this ancient, radiation-scarred surface. The intense carbon dioxide emission would be the peeling of this cosmic sunburn, revealing a potentially more water-rich interior underneath that the sun's heat has not yet reached. This hypothesis is compelling because it accounts for the comet's extreme age and its unimaginably long journey. It suggests that interstellar comets are not static time capsules, but evolving bodies, their surfaces slowly cooked and transformed by the galaxy itself. Without radar to measure the density and thermal properties of the nucleus, we cannot distinguish between these scenarios. We are left with a chemical ghost, its true nature obscured by distance and time. The story does not end with carbon dioxide and water. The James Webb Space Telescope's near-infrared spectrograph detected other molecules. a supporting cast that adds crucial depth to the mystery. It found carbon monoxide, CO, outgassing at a rate of 14 kilograms per second. Carbon monoxide is a hypervolatile, meaning it turns to gas at even lower temperatures than carbon dioxide. Its presence in comets is a key tracer of the coldest regions of a protoplanetary disk. The ratio of carbon monoxide to water in 3I Atlas is also exceptionally high, reinforcing the idea that it is a truly cold-formed object. More intriguingly, JWST detected carbonyl sulfide, OCS, a sulfur-bearing molecule that is rarely seen in such abundance in our own solar system's comets. The presence of significant carbonyl sulfide suggests a unique sulfur chemistry in its parent nebula, perhaps one with different temperature and pressure conditions than our own. These minor species are the fine print in the chemical contract, and they all point to an origin that is fundamentally alien. The ultimate chemical fingerprint, however, lies in the isotopes. Isotopes are versions of an element with different numbers of neutrons. For example, most hydrogen has just a proton in its nucleus, but a rare isotope, deuterium, has a proton and a neutron. The ratio of deuterium to hydrogen, the D to H ratio in water ice, is highly sensitive to the temperature at which that ice formed. Colder formation environments lead to a higher D to H ratio. Measuring this ratio in 3I Atlas would be a direct test of its formation temperature. Our solar system's comets have a wide range of D to H ratios, some similar to Earth's oceans, others much higher. Finding a ratio in 3I Atlas that is wildly different, either extremely high or extremely low, would be conclusive proof that it formed under conditions not found in our solar system's comet-forming regions. Likewise, measuring the ratios of carbon-13 to carbon-12 diazose, or nitrogen-15 to nitrogen-14 diazose, would provide independent clues about the chemical and radiation environment of its birthplace. These measurements are at the absolute limit of JWST's capability and require many hours of observation. The data from August and September of 2025 are still being analyzed. The answer to whether this comet is just from a cold place or from a truly alien place may be hiding in those isotopic signatures. Beyond the gas, there's the dust. The images from the Hubble Space Telescope revealed a classic teardrop-shaped coma and a faint dust tail. This dust, composed of tiny solid grains lifted from the nucleus by the sublimating gas, is as much a part of the comet's story as the ice. What is it made of? Are the grains fluffy aggregates of silicates and carbon, like in our comets? Or are they different? The James Webb Space Telescope's mid-infrared instrument, MIRI, is designed to answer exactly this question. MIRI can study the thermal emission from the dust grains, revealing their composition. Silicate minerals, for example, have a distinct spectral feature around 10 micrometers. The shape of this feature can tell scientists whether the silicates are crystalline, like sand, or amorphous, like glass. Crystalline silicates require high temperatures to form, suggesting they were processed near a young star and then transported to the cold outer disk. Amorphous silicates suggest a more pristine, unprocessed origin in the cold. Analyzing the dust of 3I Atlas could reveal the processing history of its home nebula. If its dust composition is radically different from our own comets, say far richer in carbon in the form of graphite or tholins, or containing exotic mineralogies, it would further cement the idea that the building blocks of planetary systems vary significantly across the galaxy. This brings us to a far grander, more profound implication. For billions of years, objects like 3I Atlas have been crossing the gulf between stars. They are galactic messengers, physical pieces of one solar system delivered to another. This reality is the foundation of the theory of panspermia, the idea that life itself could be transported between stellar systems. While 3I Atlas is almost certainly not carrying life, it is a perfect test case for the vehicle. Could a microbe frozen deep within its nucleus survive a 4.6 billion year journey? The challenges are immense. The same cosmic rays that alter the surface chemistry would deliver a sterilizing dose of radiation thousands of times greater than anything life on Earth could withstand. The absolute cold would preserve organic molecules, but would likely shatter complex cellular structures. The final arrival, involving heating and outgassing, would be another perilous filter. Yet nature is resilient. If the nucleus were large enough, say several kilometers in diameter, its deep interior could be shielded from the worst of the cosmic radiation. Water ice itself is an effective radiation shield. A microbe trapped 100 meters deep might experience a significantly lower radiation dose. The primary threat would be the slow, steady accumulation of damage from natural radioactivity within the comet's own rock, and from secondary particles, created by the most energetic cosmic rays. The journey is long enough for even this low-level radiation to become lethal. Most scientists believe that a 4.6 billion year transit time is simply too long for any known form of life to survive. However, the discovery of 3I Atlas proves that the transport mechanism is real. The galaxy is cross-pollinating itself with the chemical ingredients for planets. Every year, thousands of these objects likely pass through our solar system undetected, carrying water, carbon, and complex organics from countless other stars. We may be chemically related to star systems hundreds of light years away, our planet's early inventory of volatiles potentially supplemented by these ancient visitors. The frustration of being unable to study. 3I Atlas up close has galvanized the scientific community. We were caught unprepared by Oumuamua. We were too far from Borisov. We are helpless to do anything but watch 3I Atlas fly by. This cannot be the state of affairs for the next visitor. The Vera C, Rubin Observatory, set to begin its legacy survey of space and time in 2026, will scan the entire sky every few nights with unprecedented depth. It is expected to find not just one interstellar object every few years, but several per year. This will transform these visitors from rare curiosities into a new population of astronomical objects to be studied. In anticipation of this, the European Space Agency has already approved a mission called Comet Interceptor. Scheduled for launch in 2029, it will be a new kind of mission. It will not have a predetermined target. Instead, it will travel to a stable gravitational point in space, about 1.5 million kilometers from Earth, and wait. It will park in space, dormant, for years if necessary. When the Vera Rubin Observatory or another survey finds the next pristine, long-period comet, or ideally, the next interstellar object on an inbound trajectory, Comet Interceptor will be ready. With months or even a year of advance warning, controllers will command the spacecraft to fire its engines and begin a journey to fly by the object. It will deploy 2 smaller probes to get even closer, creating a multi-point snapshot of the object. Its nucleus, its gas, and its dust. It will be our first dedicated attempt to ambush a visitor from the depths of space. It is a mission born from the frustration of watching objects like 3I Atlas pass by, their deepest secrets sealed by distance. 3I Atlas, therefore, represents both an end and a beginning. It is the end of our ability to study this specific object in detail. By March of 2026, its brief encounter with Jupiter will be over, and it will be flung back out into the galactic night, never to be seen again. Its trajectory is a one-way ticket, but it is also the beginning of a new understanding. It has shown us that the chemical diversity of planetary building blocks in the galaxy is far greater than we imagined. It has proven that the oldest relics from the galaxy's formation are still wandering among the stars, waiting to be found. It has underscored the profound loss of Arecibo and the urgent need for more powerful planetary radar systems, and it has served as the final hourglass, definitive argument for why we must be ready for the next one. Because the secrets hidden in a comet we can only study from afar are the secrets of our own cosmic origins, scattered across billions of stars and billions of years.